Okay, question 10. So this is the required practical. I really wanted to make sure I had this video done and ready for you the night before the exam at least, because we know there's going to be a question on refraction and reflection on the triple paper. So this is one on refraction, but reflection is dead easy. So before we start on the refraction, I'll show you about reflection. So reflection involves a plane mirror, and I represent a plane mirror like this. And you would have a light that shines in. But before we do that, we have to establish a normal line. So a normal line is one that is at 90 degrees to the boundary. We represent a normal line though with a dashed line, so I'll use a dashed line. I don't have a ruler on the iPad, unfortunately, so it does affect my ability to show you how to draw a dashed line. I'm going to shine a light in to this angle of incidence. And that's what we call the light that we shine in. And we're going to hit that boundary between the normal line and the mirror. So you have to always put an arrow on to show which way the light is going. So that here is called the angle of incident. All right, the incident angle. And if you use the word in, because it goes in. Now, that will reflect off, and we'll use a different colour for this one to show you the reflection. Let's use a blue. So that will reflect from that same way at exactly the same angle. And that is called your angle of reflection. All right, and the rule is that the angle of incident is equal to the angle of reflection. So if you get asked about that practical, that's it. You're just shining it in. You'll notice, and it's a bit frustrating, and it's just the way that my iPad done it. I've missed this slightly. Let's see if I can adjust that. No, I can't. Without moving that, let's see if I can just really. No, unfortunately, I can't move those lines, but I should be hitting exactly on that boundary, and it would look a little bit more obvious. Maybe I can move this. Oh, yeah, there we go. I'll cheat a little bit so you can see I'm now hitting exactly on that normal line. And if I was to do that, it would look a little bit more. There you go. You can see that the two angles are identical now. So shine in, hit the boundary between your normal line. Let me label that as the normal line. The normal. And remember, your normal line is at 90 degrees to the boundary. So shine the instant in, shine your reflected ray goes the other way. Remember to include these arrowheads. They're really important to show which way the light is traveling. People miss them out and lose marks that they definitely should have got. So let's focus on the other practical then that you could be asked about, which is refraction. So that is reflection. Let's look at refraction. So we're shining a light, and as you see, just like I've drawn there, this line here is our ray. So it's going like that. Now the question is, the ray of light should be as narrow as possible. Explain why using a wide array would give a less accurate result than a narrow array. And this is just about uncertainty. So uncertainty is like how confident you are with with your results. Now, if so, a wide array would be harder to work out. Yeah. So if I was shining a ray into this, and I'm looking at this normal line, and I'm measuring that angle. If my ray was bigger, I'll just over the top like that. Right, all of a sudden, my ability to measure this angle isn't as certain as it once was. So the wide array, just like that's harder to read when I use a wider pen. Wide array would be the harder to judge where the center is, because when we do this experiment, you have to draw the lines. So in order to do those lines, you end up putting some dots and connecting rays. I'm going to show you that in a second when I talk about the practical. But the wide array would be harder to judge where the center is. So the uncertainty of the measurements taken would increase. You see, it's probably getting late now, and my brain's starting to break down a little bit, but something like that for your 2 marks. So wide array, harder to judge where the middle is. We need to know where the middle is so we can plot a nice straight line because we're going to draw it with our pencil. And that's why it's important we use a sharp pencil during this. And therefore there'll be more uncertainty. Remember, uncertainty equals range divided by 2. So the bigger the range divided by 2, you're more uncertainty. Right, the graph below shows the results that some pupils did of this experiment. All right, you can see that I've already worked this out once. All right, so I'm going to do it again. Now, looking at that graph straight off, I know a lot of people, me included, would be tempted to be like, straight line of best fit. All right, and get a ruler and join them up. Like, all right, I've got 3 on that side, I've got 3 on that side. There we go, straight line of best fit. The problem is, as I'm looking at that now, it's very obvious to me that something's going wrong here. Right? It's verging away from that straight line here. So that isn't a straight line, that's a curved line. So what we're going to do is we're going to try and draw a curved line. So we don't need to join the points, but we just need to follow a line that's something like the points. And you can do what I'm doing here by just putting your ruler and just sort of like creating an angle in it and moving that around. So something like that. I think I missed that a little bit. Let me try again. So drawing a curved line is a bit of a skill, all right, and it requires a little bit of practice. So probably something like about there, I would say. Something like that. That's probably following the pattern pretty closely. We're just trying to I'm going to do it one more time. One more time. I'm determined to get a little bit more accurate than that. That's pretty good. All right, that's my best yet. There we go. So I think we're about something like there, maybe. Okay, have I got that curve enough? I think so. Yeah, about there. All right, so we can start to see that we've got that curve now. So it wants us to estimate the angle when the angle of incidence is 80. All right, I'm going to use a pink to make this a little bit more easy. So we draw the line up to 80. The reason we're estimating this, I don't know why I use pink. I always get weird bits like this, but whatever. The reason I'm estimating is because we haven't actually got a point there. Draw a line across. That was pretty bad. All right, and but luckily I can get a straight line. So you would use a ruler, obviously, and that allows us to get that reading. So you can say I've got 41. That's 42. Is that correct? Am I using the right scale, or am I just again jumping to conclusions? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 squares, and there's a difference here of 5. 10 squares equals 5. So 1 square divided by 10, divided by 10. So 1 square is equal to 0.5. All right, so yeah, I did just jump to a conclusion. It's not 42, it's 41. So my angle of refraction is 41 degrees. Now, I know that there will be a degree of tolerance allowed there because depending on how you drew your curve, they will give you a bit of leeway. So you're probably all right if you've got something from about 40 to 43 degrees, all right? So something along those lines. And it's worth 2 marks. So one of them you'll get, as long as you've got a line of best fit that you've extrapolated to the 80 degrees, so you know what you're doing, you'll get a mark for that. And then the second mark will be for actually drawing your guidelines and figuring out that that's 41 or somewhere in that region. Okay, so this last part, and this is the 6 marker, we have to describe. So we're not explaining, we don't need to say how, we're just saying, so what to do. So we're just saying what to do. A method, so step by step, logical, that a student could have used in order to get these results. So I'm going to go through with you the practical just in a quick drawing, and then we'll use that to go through. Before we do this, I just want to talk to you about a few things that I've learned about the marking this year, from talking to friends who are exam markers, and they've just told me a few things about what they've marked in paper so far. So one thing is the working out. That's definitely needs to be seen this year, and they're being very strict on that, and they want to see working out. The other thing is to do with these required practicals. They really are looking at you getting this spot on in terms of in order to access those the 4 to 6 marks. They want you to make sure that what you have described could be reproducible and could have got those results. And you've got to mention the pieces of equipment that you're going to use each time. So it's not good enough to just say, oh, measure the line. You have to say measure the line using a ruler. You can't just say measure the temperature. You must say measure the temperature using a thermometer. So that's the kind of feedback that I've been hearing. So take that in mind with you to the exam. So with this, it all starts out by getting a piece of paper. So you're going to get yourself a piece of A3 paper like that. And then what we do is we get our glass block, and I'm going to make my glass block a bit of a lighter colour so you see, and we place it on our A3 paper like that. That's probably not very easy for you to see. Let me use a better colour. All right, for some reason I'm going to have an orange glass block just so you can see it. All right, so we place it on the paper. So step one is to place a glass. You could also use perspex, but that's fine. A glass. Did they say it was glass? It didn't say what it was, so you could say perspex. So place a glass block on a piece of A3 paper. That's just step one. And again, if this is the night before the exam, I'd be learning this by rote and writing it out over and over again until you get it, and then you just take that into the exam and get that in your head tomorrow morning before you see that paper. So place a glass block on an A3 piece of paper. The next thing you have to do is, because at the end of this you want a diagram and you want to see and be able to measure your results. So that glass block you're gonna have to lift up. So you have to draw around the glass block. So I'm gonna try and do that now. So I'm gonna get my black pen, and you just draw around your glass block like that. So step two is to draw around the glass block. Again, mention the what you use. So in pencil, right? It might not be the most important thing, but you're making sure each time saying what to do and what to do it with. Step three. So the third thing we're going to use is we're going to go back to this, and we see we've got a ray box. We need a ray box. So we get a ray box and we shine it at the glass block. Now, before we do that, all right, what we need to do is we need to establish this normal line. So I'm going to draw my normal line on. I'm going to do my normal line in green. Remember, the normal line is a line at 90 degrees to the boundary of the object, so the glass block in this case. So you used a dashed line with a ruler to draw on your normal line. So that's step three. Draw a normal line dashed at 90 degrees to the boundary of the glass block. That's important because we need to know where we're going to shine our ray. And then we get our ray box, and the ray box is connected into the oh, I've drawn a circle. That was a very bad box. Let's try again. Box. Right. So now we've got our ray box, and the ray box will emit a light like this. All right, a nice straight line. Now you can see I've not hit what I want to hit. So I did that on purpose because we get our ray box and we've got to shine the ray box so that the light hits the boundary of the glass block and the normal line. So I'm going to shine it there. I'm just going to label that as the ray box. And we have to put an arrow on to show which way that the light is shining. So if we then measure this angle here, this gives us the angle of incident. Okay, so 4 is to shine a ray of light at the boundary of the glass block and normal line using a ray box. So shine a ray of light using a ray box. Now, again, a reason I've done that in pink is because you need to then draw that line on it. So what you do is you mark 2 points on that line, and then when you turn off the box, so let me turn off the box by getting rid of it. There you go. The ray box is gone now. And I'll take away the arrow as well for this point. And then what you can do is when you're drawing your line, is you just need to make sure that your line goes on those 2 points, and then you've got the same line that your ray box produced. Again, just put the arrow on to show it. So when you turn off your ray box, you've still got that produced, and you would see that on your A3 piece of paper. All right, so that's 5. Now, as again, we haven't got enough room here to write this 6 marker, but you've got that piece at the back of your page where it says you can add extra. So I would definitely be going like this. So 5 is to draw 2 dots on the ray to indicate the position of the instant ray, and then join these with a ruler. All right, so then you'll get that. Then what you do is you measure the angle of incident, and you do that with a protractor. So measure the angle of incidence with a protractor, and you can see that that gives us one of our results. So if I measured that, if that was 45 degrees, you would see that that's my angle of incidence. So I would be plotting that on my graph at the 45-degree point. So now I need to tell them, well, how do I get the other part? How do I get my angle of refraction? So let's explain how to get that. So what will happen at this point is when the ray box is being shone in, so we'll put the ray box still shining our light in. Go back to that pink line. You won't be able to see underneath this glass block, but what you will see is you'll see another ray coming out at the same angle as that one went in, like that, on the block. And what you do is you do the same thing. You mark the center of the ray. So you know that question back here was talking about uncertainty. The wider that ray is, the harder it is to get the dots in the middle. So more uncertainty. So you mark the 2 dots again, and you trace over them again, and you put your arrow on again to show that. And again, when we get rid of that pink line, I've just got rid of both lines, but it's okay because we've got our dots still. So we put our lines back in, our line back in again. Missed it. There we go. So when we get rid of that line, what we can see is we've got a that doesn't join up perfectly. In fact, it does. So I've drawn my diagram a little bit wrong. Let me just change my diagram a little bit. Go back a few steps. So what we should see, just to move it over a little bit, is the ray box coming out something like that. And so it shouldn't come out in a straight line. Again, put our dots in the middle. Okay, join it up. Draw our arrow on. So when we are just left with the black lines, what we can do is we'll then join the middle points together like that, and we can see that now actually that line has bent a little bit, and that's the whole point of refraction. The line bends a bit. If it was a straight line, it would have gone like that, and it hasn't. It's bent, and it bent when it went through the glass block, because refraction happens at the boundaries between different densities, and basically what happens is the light gets slowed down as it goes through the medium of different densities, which causes it to bend. In this case, it's bent towards the normal line. So in order to get that data, what we would do is we would then just measure this angle, and this is the angle of refraction. Okay, so let's add that to our method, all those steps. I know I got a little bit convoluted there, but we'll find out where we're back to. So 6, measure the angle of incidence with a protractor. Okay, 7 is to place dots on the line, so on the ray coming out of the glass block, and join with a pencil. What I'm going to do is I'm just going to shrink this text down a little bit so I can carry on going. Right, normally I would just obviously jump onto the next page, but I want to keep it on one page. So I'll put it over here, and then we can do our second part of the method over this side. So we're up to 8, step 8. So place the dots, join it with a pencil, and then it's the join the middle. So join the 2 rays together using a ruler, and that's the under the glass block. So join the 2 rays together using a ruler, the area under the glass block. And 9, measure the angle between the refracted ray and the normal using a protractor. And that will give you the angle of refraction. And then you plot that point on the graph. So 10, plot on the graph. And 11, the last step, the student hasn't just got one result on the graph, they've got multiple. So you just repeat. We will repeat for different angles of incident. Yep, so you would just do it a couple of times where, next time you shone the light in, we'll use a purple line, at a different angle, like that, and then you would get a slightly different angle of refraction, like that, and then you would do it again at another angle coming in, which is a red line, like that, and you would just keep doing that, and you would keep getting different angles of incidence from your normal line and different angles of refraction from your normal line, and you just plot them on a graph, and you would get the results that the student did. Okay, D. The student repeated each measurement 3 times. Go back to my green pen. When the angle of incidence was 40, the three measured values of the angle of refraction were 28, 25, and 22. Estimate the uncertainty in the angle of refraction when the angle of incidence was 40 degrees. So, remember, I said this earlier, uncertainty. I don't know why I'm writing up there. Uncertainty is range divided by 2. So the range of these results is the largest is 28 and the smallest is 22. So our range is, again, even if it's easy, even if you're looking at it going, I know what the answer is, I know what it is, absolutely, in my head, don't worry, you're in an exam. You only got one chance to do it. 28 minus 22. Yeah, we knew it was 6. We knew it was, but we have to check. So a range is 6. So it's range divided by 2. So 6 divided by 2 would give us an uncertainty of plus or minus 3 degrees. And the last one, what property of the light wave changes when it is refracted? And that will be the velocity. Because as we said there, when we shine light into different densities, let's say that's glass. All right, I'll just try and explain this in case you get a wavefront diagram. So let's say we've established our normal line. We're going to put 2 of them on because I'm going to show you a wavefront diagram. So I'll use fancy pink pen again. So let's say we've shown our line in and we've hit that normal. Okay, what happens is that the light will start to slow down. But the light, remember, is a ray. So we will also have, it'll be made of a wave. I'll try and show that to you. So we can put a second normal on here. So that wave is represented by the peaks. So imagine we're doing a wave like that. And all you can see is you're looking down and you are just seeing these peaks. So that's what I'm representing here. So you can see that the distance that these peaks are away from each other represents the speed. So the closer together, the faster they are. The further away they are, the slower they are. Now this bit here, let's call this bit A. Let's call this bit this B. You can see that A of this wave hits the glass before B does. So it is going into glass. It was in air. So in air, the light can move quite quickly because there's less particles. Air is less dense, so it can move through the air quite quickly. But when it gets into the glass, it gets slowed down. There's lots of glass. Glass is very dense. It slows those particles down. So A will start to slow down, whereas B is still going quite quickly. So what will happen is it will curve in. So like we'll say towards the normal because A slows down first. So what you do is you just sort of draw that line happening. So it's slowed down. And then we follow that down, so we'd have our refraction like this. So you could be like, all right, well, A slowed, and then we have they're going to get closer together, sorry, because now they're going slower, so they're getting closer together. So A would join up to that one here, and then the next one will be like that, and you can see now that it's caused that to change direction and they're closer together. And then the same thing happens again when they come out. A hits before B, so A speeds up faster than B does. So A starts to be further away, like that. And that's what we call a wavefront diagram. And that's what explains what refraction is. So the reason why it bends is because the speed of the light changes. And if we think of light being a wave, that explains why it bends. So the answer here is velocity. Okay, that's the last question I'm going to do on this paper. Good luck in your exam, and hopefully this has been of help to you.